Hi everyone! Today we're going to be looking at finding the area, in other words, estimating the area under a curve. So let's say we have a curve like f of f, and in calculus, finding the area under a curve that is bound by the graph, the x-axis, and any two x values. So the two x values I'm going to talk about, let's just call these two x values a and b. So I want to find the area that is underneath this curve, in between the curve and the x-axis, and then bounded by a and bx values. So what I'm trying to do is I'm trying to estimate the size or this area. So question of the day is, what is this area? Now, up until now, we've calculated area for objects like squares. So we can find area of, you've calculated area of squares before. There's a formula for that. You've calculated the area of circles, triangles, trapezoids, lots of geometric shapes we've calculated areas for, and we calculated all of these areas because we had formulas. The problem is this is a curvy shape, and it's not any of the geometric shapes that we found areas for in the past. So we have to come up with a way to estimate this area. So one method of doing this, of estimating it, is by using rectangles. And so what that means is I can try to say, okay, well, I don't know the area of this like curvy region, but if I divide this region into a set of rectangles that touch the curve or get as close to the curve, maybe a little bit taller, as close to the top of the curve as I can, then I might be able to come up with a good estimate of the area under that curve. Now with this particular drawing that I've drawn, I can see that the rectangles take up most of the area under the curve, but there's still a little bit of parts over here that I didn't quite hit. But it gives me a number that's pretty close, but not the exact area. And looking a little bit further, there are three different ways that we can look at using rectangles to estimate the area. And these, whenever we use a rectangle, we call it a Riemann sum. There are three different ways I can do it. The first way is with a left endpoint. And the left endpoint means that the left vertex, or the top left vertex, is on the curve. If it's called a right endpoint or a right Riemann sum, then the right vertex is on the curve. And if I notice with the left vertex is on the curve, I've got this extra space that didn't get covered. And when the right vertex is on the curve, then there's some overhang. So another option is to use the middle part. Is on the curve. And hoping that when we use a rectangle with the middle point on the curve, then maybe some point that's under gets kind of canceled out by the area that's on the outside. Again, it's not going to provide a perfect estimation, but it gets pretty close. The other method that's been done is called a trapezoidal sum. And so instead of dividing that area under the curve up into rectangles, they divide it into trapezoids. And the trapezoids all look like this. And remember, a trapezoid has to have one set of parallel sides, and the parallel sides are the bases. So base 1, base 2, and then the bottom that's on the x-axis is going to be the height. So here you'll draw the trapezoids and make sure with the top vertices need to touch the curve. So you'd find the area of each trapezoid and add it all up. And you'll need this formula later. The area of a trapezoid is 1/2 base 1 plus base 2, or 1/2 times base 1 plus base 2 times the height. So let's look at just sketching a couple of Riemann sums, and then we will estimate some area. And whenever we estimate the area under the curve, so when we estimate the area under a curve, what we're actually doing is we are estimating the value of a definite integral. So if we take our rectangles and we use more and more and more of them with smaller widths, we can get an even better approximation. In fact, we could actually have infinitely many rectangles under there. And if we consider taking a limit of accumulating infinite rectangles, we arrive at the exact area under the curve. And the exact area under the curve is called the definite integral. And here's the notation for that. It looks like this. You have your symbol. This is your integral symbol. The numbers at the top and the bottom are called your limits of integration. The bottom number is where your x value of that where you start, or your t value because we're with respect to t. So start at t equals 0. And this means to stop at t equals 5. The d of t part, or dt means, not d of t, dt means with respect to t. So we're going to take an integral with respect to t. And r of t is the name of the function. So if I were to imagine a graph like this, here's my x and y axis. I'm going to draw a curve for r of t. We'll call this curve r of t. The integral would start at 0. It would stop at 5. And the integral would give me the value of the area between the x-axis and the curve. Now, we don't know how to do this algebraically yet. Today, we're just working on using rectangles to estimate that value. So let's practice some rectangles. Here, we're going to let f be a function that's graphed below. We're going to make 6 subintervals, which means we need to make 6 rectangles. Equal length. And it's going to represent a right Riemann sum. So I want to make sure I do a right sum. To figure out the length of the subintervals, I can look at the 7 and the 1. So I'm going to do 7 minus 1 divided by the 6, because that's how many rectangles I want. So I'm going to go from 1 to 7, and I need to divide that up into 6 rectangles. And they need to be equal length, so that's why I'm dividing them by 6, which gives me 1. So each rectangle is going to be 1. Then I need to draw them so that the right vertex of the rectangle touches the curve. Right vertex, touch the curve. Right vertex, touch the curve. And I'll continue this until I get to 7. Right, touch curve. Okay, and then I can see that this estimation, if I estimate all of the area of these rectangles and add them up, I'm going to get a value that's much larger than the area under the curve and above the x-axis. So I would call this an over approximation. Let's see what happens with a left Riemann sum. So this time I'm going to make 3 subintervals and a left Riemann sum. I'm going to go from 2 to 5. So the width of each subinterval, I'll take the 5, subtract the 2, because I'm going to go from 2 to 5, and divide that up into 3 subintervals, which again is 1. And this side, the left side of the rectangle, needs to touch the curve. And then I'll draw those in. And if I were to find the area of each rectangle and add it all up, it would be much less than the actual area under the curve. And we call this an under approximation. Okay, so now let's look at a word problem. Let's do the whole thing. Table below represents the velocity in feet per second of a car traveling on a straight road over a 50-second time interval. And I look at the graph, and I look at the horizontal axis, I see 50 seconds, and it represents the velocity. So this unit is going to be feet per second. I always like to take some time and make sure I really understand what's happening. So if I look at this data point at 20 seconds, the car is going 52 feet per second. Okay, we want to estimate the distance the car traveled over this interval using right-hand sums and left-hand sums, along with 2 different approximation techniques, the midpoint and trapezoid rules. We'll use the table with our graph for our computations. Okay, so let's estimate. We want to do, on part A, 5 partitions of equal length, and I want to start at 0 to 10. So I'm trying to estimate the integral from 0 to 50 of v of t dt. So I'm going to draw some left-hand rectangles, which means the left hand needs to be on the curve. Oh, that first rectangle is flat. Second rectangle. The third rectangle. Maybe I should make these different colors. Well, I'll do that in a minute. The fourth rectangle. And then the fifth rectangle. All right, so I need to figure out the area of each rectangle. So let's first start with this first one. I see that the length or the width at the bottom is 10, and the height is at 0. So I look here, and I see that my height is 0. So 10 times 0 for the first rectangle. I'm going to add that for my second rectangle. The width again is 10. To get the height, I need to know the y value right here, which looks from the graph to be 20, but I'm going to go to the table and see when t is 10, the y or the v of t value is 20. So I see this is 20. So 10 times 20 plus, for the third rectangle, the width again is 10. The height I'll get from this point, which matches up to when t is 20. The v of t value is 52. So this height is 52. So 10 times 52 plus another width of 10 to get this height. I need to use when the t value is 30. The y value is 80. So 10 times 80 plus, for my very last rectangle, x value or the t value is 10, and the height goes right here when t is 40, y is 77. So 10 times 77. So I'm going to use my calculator. I'm going to type all that in. 10 times 20 plus 10 times 52 plus 10 times 80 plus 10 times 77. I get 2290. And when I think about units, I multiplied, I can come over here for each one. For each rectangle, I took my 10, which was measured in seconds, and my height was measured in feet per second. And when you multiply your length, which is in feet per second, times your width, which is in seconds, the seconds cancel and I have feet as my answer. So feet. So according to this estimation, the car traveled 2,290 feet in 50 seconds. And I can tell because there's still a lot of area left over underneath, it's probably even more than that. Now let's try using a right-hand sum. So I will pause this, draw the rectangles, and come back in just a second. So here are the right-hand rectangles. Notice that the right vertex is now on the curve. So now I'm going to calculate my right hand. Let's see what happens when I estimate it. I wonder if it will be the same. So I'm going to estimate again the same thing. I'm still estimating the integral from 0 to 50 of v of t dt. And it is approximately. So for the first rectangle, width is still 10. The height is now at this point, which has a v of t value of 20, plus for the second rectangle, width is still 10, but this time the height is at 2052. So 10 times 52. The third rectangle still has a width of 10. The height is where t is 30, so the height is 80. So 10 times 80. The fourth rectangle, width is still 10. Height I get from when t is 40, so 77. Plus this last one, width is still 10, but height is now when t is 50, height will be 74. So let me grab my calculator and I will estimate all that up, or multiply and add. I'm going to multiply 10 times 20 plus 10 times 52 plus 10 times 80 plus 10 times 77 plus 10 times 74. And I get approximately 3030 feet. And here I can see the rectangles kind of hang over more than there's under. So this looks like an over approximation. So I could say that between the two, the car traveled somewhere between 2,290 feet and 3,030 feet. Sometimes you'll have examples where you just have a table and the subintervals are not always equal. They're just indicated by the table. So I have a left Riemann sum and the subintervals are being indicated by the table. So what I like to do, I don't have a picture. I know I'm going from 1 to 9, and each one of these is a subinterval. So I have 1, 2, 3, 4, 5 subintervals from the table. So what I like to do is I like to kind of sketch something. I'll put the x values that are given. So there's a 1, a 2, a 4, a 5, a 6, and a 9. And then I make a curve And I have to make sure it makes a difference. This time I want to do a left Riemann sum. So that means the left vertex is going to be on the curve. So this, for this one, the vertex would be where the 1 is. So for this red rectangle, the width of the rectangle is 1. The height goes for where x is 1. So the height's going to be 2. This 2 right there tells me the height. When I go to make my next rectangle, I go from 2 to 4, so the width is no longer 1. Now my width is 2. And it's a left Riemann sum, so the height comes from the left endpoint. And so that is 6. So right now when I'm estimating the integral from 1 to 9 of f of x dx, I have the area of the first rectangle 1 times 2 plus the area of the second rectangle 2 times 6 plus, now let's go into the third rectangle. Width is 1 again from 4 to 5. Then when I draw my rectangle on the curve, now remember I just sketched this curve in, so these heights are not going to be accurate. But I have to look on, for the height, where the x value is 4. So for this 4, it will be 13. So 1 times 13. The sketch is just here to help me make sense of some of these numbers. From 5 to 6, the width is 1. The left side is going to determine my height. So that height is here, 18. So plus 1 times 18 plus, let's see, from 6 to 9, that width is 3. And the height is determined by the left side. So I need to look at the y value for 6. 3 times 23. I multiply and add all of these up. So I've got my calculator in my hand right now. I am typing 2 plus 12 plus 13 plus 18 plus 3 times 23. 114. It's approximately 114. Get some practice with this. Let me know if you need any help, and have a wonderful day.